Today we're talking about energy in quantum mechanics. But don't worry, you don't need any background in quantum to understand this video. By the end, you'll know some incredible facts about quantum mechanics that even some physics majors in college don't know about. I'm Scott, I'm a physics and math teacher. Let's get started. So in part 1 of this What is Energy series, I defined energy as a scalar conserved across a boundary in many different forms that models a system's behavior. In part 2, I said that many people define energy as the ability to do work. And although this definition is adequate in most situations, it's not perfect. But there's actually a third definition of energy, one that comes from quantum mechanics. It defines energy as the eigenvalues of the Hamiltonian, which is the generator of the time translation operator. Now, you probably looked at that and said, what? The rest of this video is dedicated to breaking down this definition bit by bit, and by the end, I promise you that you'll be something of a quantum mechanic yourself. So in order to explain every part of this definition, let's start at the last part and work our way back. In other words, let's start by explaining what an operator is. An operator is a mathematical device that takes a function and transforms it into another function. One example of an operator is the derivative operator, written as d dx. Let's take a function like x squared and apply the derivative operator. We end up with 2x. So one function goes in, x squared, and one function comes out, 2x. Just to be clear, operators and functions are different. With a function, a number goes in and a number comes out. For example, y equals 2 to the power of x. If I put in x equals 2, I get out 2 to the power of 2, or 4. A number goes in, that being 2, and a number comes out, that being 4. With an operator, a function goes in, like x squared, and a different function comes out, like 2 times x. So that's what an operator is, but what's a time translation? And what's a time translation operator? The term time translation is actually a lot more straightforward than it sounds. It's just a fancy term that means changing the moment in time. If you hit the 10-second skip button on a YouTube video, for example, then the video has just undergone a 10-second time translation. Similarly, if I pick up a remote control and rewind a movie 5 minutes, then that's also a time translation of -5 minutes. So what's a time translation operator? It's an operator, as defined a moment ago, that changes the moment in time that we are interested in. You can think of it as being the mathematical representation of a remote control for the universe. This mathematical representation might look terrifying at first, but it's actually a lot simpler than you might initially assume. So it says that suppose we have some physical system that's described by some function, x, at some time t. Now suppose we apply the time translation operator, capital T, and it changes the time by some amount a. Well, that results in a physical system that's described by some function x at a time t plus a. So this is basically the mathematical way of writing the 10-second rewind button on YouTube. This is all very abstract, so let me provide a concrete example. Suppose you have a bucket of water, and when your stopwatch says t equals 0 seconds, the ripples of the water in the bucket kind of look like sine of x. Now suppose 2 seconds later, the ripples in the bucket look a little different, and the water's ripples look like cosine of x. In that situation, we would say that sine of x acted upon by the time translation operator of 2 seconds equals cosine of x. Just to be clear, this is not generally true, but it's true in this particular case. At this point, I want to pause and acknowledge that the math here can be a little intimidating, and that's perfectly normal. This is the kind of mathematics that I didn't see until grad school, so the fact that you're here and you haven't clicked away means you have incredible fortitude, and that's a really admirable trait. Like I said earlier, if you watch until the end, you'll know something about quantum mechanics that even I didn't know when I graduated with a bachelor's in physics. So with that in mind, let's get back to defining energy in quantum mechanics. So we've gone over operators, time translations, and the time translation operator, but what is a generator? To answer this question, we'll need the help of this guy. This is Marshall H. Stone, a mathematician who published an equation in 1932 that turned out to be incredibly useful in quantum mechanics. The equation is called Stone's theorem on one-parameter unitary groups, or just Stone's theorem for short. It states the following. Suppose you have some operator. In our case, let's suppose this operator is our good old time translation operator t. If there's an operator, Stone's theorem says, then there must also exist some second operator. We'll call it h. Stone's theorem then tells us that this first operator, t, and this second operator, h, are related to each other by the following equation. T equals e raised to the power of I h little t over h bar. Let's break this equation down step by step. Big T, as mentioned earlier, is an operator. For our example, we chose it to be the time translation operator, but there are actually a bunch of different operators in quantum mechanics that we could have chosen from. E is Euler's number. It is a constant 2.718281828, and then it goes on forever. It's a number that shows up all the time in calculus. H is the second operator. We call it the Hamiltonian. We'll return to the specifics of what it is and what it does in a moment. I is the imaginary unit. It is the square root of -1. Little t is the value that the operator changes. So in our case, t is the time translation operator, so therefore little t is time. H bar is a constant. Now, Stone's theorem actually does not tell us what the constant is, it just says it's some unknown number. To know the value of h bar, we have to do real-life experiments, and physicists have experimentally found that the constant is 1.054, and then it kind of keeps going for a while, times 10 to the negative 34 joule seconds. H bar is also called the reduced Planck constant. But that being said, we get the value from real-life experiments, not from pure mathematics. So that is Stone's theorem. It basically says that the time translation operator t has a buddy. His name is h, also called the Hamiltonian. I promise I'll explain more about this mysterious operator soon. But first, I promised to define the term generator. Physicists say that h is the generator of t because Stone's theorem also works the other way. If we start by assuming that there exists a universe and it's described by a Hamiltonian operator, therefore there must also be, by Stone's theorem, a time translation operator. In other words, you can say that the Hamiltonian generates time translations. It is the generator of the time translation operator. Quick side note, this theorem only works if the laws of physics stay the same over time, which is true in almost all real-life situations. If the laws of physics are dependent on time, then we have to use this equation. But luckily for us, we can use Stone's theorem in the vast majority of situations. So to recap, we've talked about operators, time translations, and generators, but there's more to say about the Hamiltonian, and we haven't even touched on eigenvalues yet. Let's talk about the Hamiltonian first. What exactly is it, and what does it do? I would argue that the Hamiltonian is the most important operator in all of quantum mechanics. The Hamiltonian shows up in a bunch of crucially important quantum equations, such as the time-dependent Schrödinger equation and the derivative of operators. The Hamiltonian is also used as a stepping stone in deriving a huge number of equations, such as Ehrenfest's theorem. It's a quantum equation that actually explains the origin of momentum equals mass times velocity and force equals mass times acceleration. In other words, a huge number of physics phenomena exist as a direct result of the Hamiltonian, including phenomena we see on a daily basis. Quantum mechanics does not just affect the very small, it also explains why classical everyday physics is the way it is. I could go on for hours talking about the Hamiltonian, but the purpose of this video is to define energy. So there's one piece of the puzzle missing, and that is, what are the eigenvalues of the Hamiltonian, and what is an eigenvalue in the first place? To explain what an eigenvalue is, let me give an example. Let's take a look at the derivative operator again, and suppose we have some function like e to the power of 2x. The derivative of this function is 2 times e to the power of 2x. So what we have is an operator times a function, and that equals a scalar constant, a number, times that very same function as earlier. More generally, we can write this equation as operator times function equals scalar times same function as before. Whenever we have an equation that takes this form, we call the function that repeats an eigenfunction. I don't speak German, but I've been told that eigen is German for own or self. So since the function appears twice in the equation, we call it the eigenfunction because it's its own function. It's sort of the self function. Since this is the eigenfunction, mathematicians call this number here the eigenvalue. The eigenvalue is the value associated with the eigenfunction. In quantum mechanics, almost all of the operators that we deal with, like the linear momentum operator, the angular momentum operator, position operator, and more, almost all of these operators have eigenfunctions that are associated with them. And where there are eigenfunctions, so too are there eigenvalues. There are even eigenfunctions and eigenvalues associated with h, our Hamiltonian operator. We write the equation like this: h times psi equals e times psi. The eigenfunctions are written with the Greek letter psi, pronounced psi or just psi, and the eigenvalue is written with the letter capital E. Quick side note, this is assuming that the eigenfunction is not dependent on time, so notice how there is no little t in this equation. Let's take a look at this mysterious value e. What exactly is it? Well, physicists proved that e is a scalar quantity. They also showed that it is conserved across a boundary. They even showed that it comes in many different qualitatively distinct forms. And to top it all off, we've even found that this value E models a system's behavior. In short, E is energy. Oh yes, it might seem very odd, but this quantity E ends up being identical to the energy we know and love. Every kind of energy that I listed in part 1 of this series, kinetic, potential, vacuum, mass energy, they all trace their origins back to the eigenvalues of the Hamiltonian. And in fact, E is the only thing that matches the definition of energy given in part 1 in the universe. If something is energy, then it is the eigenvalue of the Hamiltonian. If it's the eigenvalue of the Hamiltonian, then it is energy. They are one and the same. So the next time you eat some food and feel energized afterwards, think the eigenvalues of the Hamiltonian. Isn't it wild that the definition I gave in part 1 and this mathematical definition end up being two ways of talking about the same thing? The universe is beautiful sometimes. We've just gone over a whole lot of information all at once, so let's rewind and review what we've discussed so far. An operator is a mathematical device that turns one function into another function. The time translation operator t is a special kind of operator that takes the function describing some physical system at some time t and turns it into a function describing that same system but at a different moment in time, specifically t plus a. Stone's theorem tells us that the time translation operator capital T is equal to e to the power of I h little t divided by h bar, where h, the Hamiltonian, is a different operator. We call h the generator of t. The Hamiltonian is an incredibly useful operator that shows up all the time in quantum mechanics. We also talked about how operators in quantum are associated with these things called eigenfunctions and eigenvalues, and the equation relating them is operator times eigenfunction equals eigenvalue times that same eigenfunction. The eigenvalues of the Hamiltonian are precisely energy, and this definition actually aligns with the conceptual definition that I prefer. There is no contradiction between them. Now, on the one hand, I just said that the conceptual definition of energy and the quantum definition are equivalent to each other. And it's true. This quantum definition is the most mathematically precise definition of energy that physicists have, and I'm not aware of any exceptions to this definition. But on the other hand, I said in a previous video that I think there's something wrong with the quantum definition. So if it's physically valid and mathematically precise, what could possibly be wrong with it? Well, in the previous video, I argued that physics is founded on pragmatism, the idea that we should define words based on what's the most educational and helpful for the recipient in that particular context. Suppose you're 14 and you're taking a high school physics class for the first time. You ask your teacher, "What is energy?" Which answer from the teacher do you think would be more helpful to you as the student? The eigenvalues of the generator of the time translation operator? Or the conserved number whose many forms help us predict what an object is going to do? I'm going to take a guess and say the student would probably get a lot more out of the second definition than the first. So that's my main issue with the quantum definition. It's not that it's inaccurate, but rather it just doesn't do a very good job conveying to the audience why physicists care so much about energy in the first place. It's not at all obvious from this definition that energy would be some physical, measurable quantity that would have an impact on our daily lives. The quantum definition is missing the why part of it, which in my opinion is the most important part. The quantum definition is perfectly true, but as a physics teacher, it's just not a very good teaching tool. And as a final thought, physicists were using the concept of energy and energy conservation at least as far back as the 1850s or even earlier, more than 70 years before modern quantum mechanics was developed. These physicists had no concept of Stone's theorem, eigenvalues, or the Hamiltonian operators, but they still had a perfectly robust understanding of energy that helped them make new discoveries and model the universe. In other words, even though energy exists as a result of quantum mechanics, that doesn't necessarily mean you need to understand quantum to understand energy. The eigenvalues of the Hamiltonian uniquely identify energy, but that doesn't necessarily mean that it defines energy, at least in my opinion. So that, citizens, is my 3-part series on energy. We have only scratched the surface regarding all of the amazing things that we can learn about the universe when we focus on energy conservation. If you want to understand the structure of atoms, the way living organisms work, or basically any electronic device, conservation of energy plays a central role in why things act the way they do. If you want to learn more about the amazing concepts in physics, stick around with this channel. Hit the subscribe button so that you'll be notified as soon as I make a new video. And if you want to see more videos like these, click the like button. This is a new channel, so giving a like or sharing the video with someone you know really helps this channel grow, and it means I'll be able to make more educational content like this. And as I stated earlier in the video, a lot of the stuff that we covered is pretty darn complex, and it confused me the first time I saw it. And so if you have any questions about what we discussed today, please leave a comment asking your question, and I'm happy to write a reply going into more detail. With that, have a great day, everyone.